1. The origin of life, from out the turning globe. Night followed day in swift succession. On Earth, at that time, a day lasted for only 5 or 6 hours. The planet spun madly on its axis. The moon hung heavy and threatening in the sky, far closer and so looking much bigger than today. Stars rarely shone, for the atmosphere was full of smog and dust, but spectacular shooting stars regularly threaded the night sky. The sun, when it could be seen at all through the dull red smog, was watery and weak, lacking the vigor of its prime. Humans could not survive here. Our eyes would not bulge and burst as they may on Mars, but our lungs could find no breath of oxygen. We'd fight for a desperate minute and asphyxiate. The Earth was named badly. Sea would have been better. Even today, oceans cover 2/3 of our planet, dominating views from space. Back then, the Earth was virtually all water, with a few small volcanic islands poking through the turbulent waves. In thrall to that looming moon, the tides were colossal, ranging perhaps hundreds of feet. Impacts of asteroids and comets were less common than they had been earlier, when the largest of them flung off the moon. But even in this period of relative tranquility, the oceans regularly boiled and churned. From underneath, too, they seethed. The crust was riddled with cracks, magma welled and coiled, and volcanoes made the underworld a constant presence. It was a world out of equilibrium, a world of restless activity, a feverish infant of a planet. It was a world on which life emerged 3,800 million years ago, perhaps animated by something of the restlessness of the planet itself. We know because a few grains of rock from that bygone age have survived the restless eons to this very day. Inside them are trapped the tiniest specks of carbon, which bear in their atomic composition the nearly unmistakable imprint of life itself. If that seems a flimsy pretext for a monumental claim, perhaps it is. There isn't a full consensus among experts, but strip away a few more skins from the onion of time, and by 3,400 million years ago, the signs of life are unequivocal. The world was heaving with bacteria then, bacteria that left their mark not just in carbon signatures, but in microfossils of many diverse forms, and in those domed cathedrals of bacterial life, the meter-high stromatolites. Bacteria dominated our planet for another 2,500 million years before the first truly complex organisms appeared in the fossil record. And some say they still do, for the gloss of plants and animals doesn't match the bacteria for biomass. What was it about the early Earth that first breathed life into inorganic elements? Are we unique, or exceedingly rare, or was our planet but one in a million billion hatcheries scattered across the universe? According to the anthropic principle, it scarcely matters. If the probability of life in the universe is 1 in a million billion, then in a million billion planets there is a chance of exactly 1 that life should emerge somewhere. And because we find ourselves on a living planet, obviously we must live on that one. However exceedingly rare life might be, in an infinite universe there is always a probability of life emerging on one planet, and we must live on that planet. If you find overly clever statistics unsatisfying, as I do, here is another unsatisfying answer, put forward by no less a statesman of science than Fred Hoyle and later Francis Crick. Life started somewhere else and infected our planet, either by chance or by the machinations of some godlike extraterrestrial intelligence. Perhaps it did. Who would go to the stake to say that it didn't? But most scientists would back away from such reasoning, with good reason. It is tantamount to an assertion that science cannot answer the question before we've even bothered to look into whether science can, in fact, answer it. The usual reason given for seeking salvation elsewhere in the universe is time. There has not been enough time on Earth for the stupefying complexity of life to evolve. But who says? The Nobel laureate Christian de Duve, equally eminent, argues altogether more thrillingly that the determinism of chemistry means that life had to emerge quickly. In essence, he says chemical reactions must happen rapidly or not at all. If any reaction takes a millennium to complete, then the chances are that all the reactants will simply dissipate or break down in the meantime, unless they are continually replenished by other, faster reactions. The origin of life was certainly a matter of chemistry, so the same logic applies. The basic reactions of life must have taken place spontaneously and quickly. So, life, for de Duve, is far more likely to evolve in 10,000 years than 10 billion. We can never know how life really started on Earth. Even if we succeed in producing bacteria or bugs that crawl out from swirling chemicals in a test tube, we will never know if that is how life actually started on our planet, merely that such things are possible, and perhaps more likely than we once thought. But science is not about exceptions, it's about rules, and the rules that govern the emergence of life on our own planet should apply throughout the universe. The quest for the origin of life is not an attempt to reconstruct what happened at 6:30 a.m. on Thursday morning in the year 3,851 million BC, but for the general rules that must govern the emergence of any life anywhere in the universe, and especially on our planet, the only example we know. While the story we'll trace is almost certainly not correct in every particular, it is, I think, broadly plausible. I want to show that the origin of life is not the great mystery it is sometimes made out to be, but that life emerges, perhaps almost inevitably, from the turning of our globe. Science is not just about rules, of course. It's also about the experiments that elucidate the rules. Our story begins in 1953 then, an annus mirabilis marked by the coronation of Queen Elizabeth II, the ascent of Everest, the death of Stalin, the elucidation of DNA, and, not least, the Miller-Urey experiment, the symbolic origin of life research. Stanley Miller was at that time a headstrong doctoral student in the lab of Nobel laureate Harold Urey. He died, perhaps a touch embittered, in 2007, still fighting for views that he had upheld doughtily for half a century. But whatever the fate of his own particular ideas, Miller's true legacy was the field that he founded on his remarkable experiments, the results of which retain the power to amaze even today. Miller filled a large glass flask with water and a mixture of gases to simulate what he took to be the primordial composition of the Earth's atmosphere. The gases he chose were believed, from spectroscopy, to make up the atmosphere of Jupiter, and were reasonably assumed to have been plentiful on the young Earth too, to wit, ammonia, methane, and hydrogen. Through this mixture, Miller passed electric sparks to simulate lightning, and waited. After a few days, a few weeks, a few months, he took samples and analyzed them to determine exactly what he